Yeah, hi. Thank you very much for this kind introduction, the perfect pronunciation of my name. I'm really happy to be here, even if it's only virtually. And I also really want to thank the organizers for putting together such an amazing workshop. I know it's very, very difficult in these pandemic days, but I still learned a lot and I enjoyed it a lot. And I'm very happy to be part of that. Having said this, I actually have two screens, and kind of like the thing I miss most is like kind of the personal interaction. So if some of you would be willing to like turn on their cameras so I can see them, I would really appreciate that. But I understand if you don't want to do that as well. And so today I'm kind of very happy and anxious to kind of tell you about some rather recent journey I did together with two very smart and talented quantum physicists, namely John Preskill from Caltech, who some of you may have heard of, and Robert Huang, who used to be a machine learning undergrad, who is now doing a quantum computing PhD at Caltech. And the work I'm going to explain today originated during my stay at Caltech, so it's kind of very close to IPAM physically. And I want to like kind of start off with like kind of a very simple and naive technique called Monte Carlo sampling for tensors. Like we all know how we would do Monte Carlo sampling for matrices. I will review that in order to get like very efficient approximations of an underlying matrix that we care about. And this idea readily generalizes to tensors. And I want to like motivate one particular way of doing Monte Carlo sampling for tensors, which might look very strange from our classical data science perspective, but I'll try to kind of convince you that the sampling procedure is actually native on a quantum computer. So what we are going to do is we will formulate a method for tensor Monte Carlo, where the difficult part is the sampling part. The data storage part will be easy, but the difficult part will be taken over by a quantum computer. And this will allow us to do the sampling task very efficiently as well and obtain very concise, efficiently storable sketches or classical shadows of quantum states. And these can then in turn be used to do data processing and discovering some phenomena of quantum nature. And more recently, we combined this machinery successful with machine learning techniques to actually do things that we wouldn't believe would be possible 1 year ago. But from a kind of like from mathematical side, the techniques I'm going to explain to you are very naive by comparison. So kind of it's a very naive idea that turns out only in the end to be a bit more powerful than you might think. And so let me start like kind of very, very briefly with kind of recapitulating what I mean by Monte Carlo sampling for matrices or tensors. And let's start with kind of like the simplest form of tensor that I'm familiar with, like kind of with a matrix, a tensor of order 2. And then the idea behind Monte Carlo sampling is to kind of take your matrix and like kind of implicitly decompose it into a sum of simple factors or contributors. In this case, I've chosen outer products or like elementary tensor products, if you just kind of go to the tensor language. And this kind of tells us that kind of in this formula, I'm implicitly approximating the matrix T by a weighted sum of outer products. And once I have this, and once I've specified such a decomposition, I can start sampling according to this probability distribution in order to get one of these rank 1 factors. And then I can form an empirical average that is written here. And just because of probability theory, the larger m, the number of samples I take, the more accurate this empirical approximation will be to the true matrix. And the hope is that there's somehow a sweet spot, that like the number of Monte Carlo samples I need is smaller than the complexity of the overall matrix. And then I can use advantageous structure in the factors to have like a simpler, more resource efficient approximation of my matrix. And the most basic and cheapest variant thereof is simply coordinate sampling. That's really cheap. Kind of like I just introduce an arbitrary factor of 1 over dimension squared, which I correct afterwards. Here's just a matrix element. And then I sample according to this uniform distribution. And I choose my rank 1 factors to be just elementary matrix spaces, like the ijth coordinate. And when I do that, I have a very, very cheap way of approximating a matrix using Monte Carlo by just randomly sampling entries and populating the zero matrix with them. And this is very, very cheap. You can do it in a streaming fashion, but you pay for it because the convergence is arguably horrible. Like there's instances where this kind of works, but you need additional assumptions like incoherence. Just try to kind of like approximate the identity matrix with such a sampling trick. It just works very poorly. And on the other extreme of the spectrum is kind of a subsampled SVD, for instance, where we pay substantial amounts of data preprocessing, executing an SVD of our matrix, which is also a decomposition into rank 1 factors. And then afterwards, we can subsample these rank 1 factors. For instance, according to a distribution that is proportional to the singular values. And then this is kind of a very good approximation of the matrix. You can quickly convince yourself. And especially if there's latent structure, if the matrix is low rank, this converges very quickly. But it's also very expensive because you have to like pre-process the data matrix. You have to do an SVD. And arguably, once you've done an SVD, it's questionable if you should do Monte Carlo afterwards even, because you might have already found a latent representation in terms of PCA. And so like with many things in life, when one is kind of too cheap and the other one is too expensive, the interesting cases usually lie in between. And for matrix Monte Carlo, my favorite example is, for example, graph sparsification. Like the problem there is that you have like a large graph with many edges, and then maybe you want to approximate it by a sparser graph, by a graph with fewer edges that can be easier stored, and it's also cheaper to run in algorithms. And if you want to do such a graph sparsification algorithm, then you should typically think in graph Laplacians. And you start with the Laplacian of a big graph, and then you decompose it into a weighted sum of elementary Laplacians that correspond to individual edges. And then afterwards, you can start removing edges at random. And this will actually kind of maintain important spectral structure of the graph and give you kind of a morally Monte Carlo model that kind of preserves interesting structure of the graph. And this has piloted us into really cool territory over the last couple of years. Like these algorithms by Spielmann and Teng for very, very efficient linear system solvers, they kind of all use graph sparsification techniques. They are a bit more sophisticated, but I think morally we can still view them as somewhere in between when it comes to Monte Carlo sampling. We kind of take the problem structure seriously, and hopefully the structure guides us towards a subsampling or sampling procedure where we can kind of get efficient sketches of the underlying thing. And now, kind of like I want to generalize these ideas to more general tensor products. And my end goal will always be the efficient approximation of certain quantum states. And so when I generalize this concept to tensors, I will already kind of implicitly suppose that the tensors I consider are kind of tensor products of matrices. So kind of you have big capital letters. This is supposed to be a matrix. And just like think of tensor products of matrices like you wish, but I will implicitly kind of work with tensor products of matrices. And I will also assume that each matrix is D by D, and there's n of them in the tensor product. And I'm interested in a case where the number of tensor factors, the number n, is much, much larger than the matrix dimension D. And in this limit, I can't use like these cool representations of tensors as a cube anymore because that only works for order 3. And so I use these beautiful wiring diagrams that I learned from the book of Landsberg. And kind of this is a representation here. I've pictured a tensor product of matrices where like each matrix has 2 indices. And so it has an ingoing index and an outgoing index. And I can like kind of, this is one dimension. And then I can represent tensor products by putting lines in parallel. Okay. And then the idea of tensor Monte Carlo is just the very same that we had for matrix Monte Carlo. Namely, we take our tensor and we choose a decomposition into elementary tensor products, like I've written here. Kind of there's no correlations, but there's a sum of them. And then once we fixed such a distribution and we've agreed on one, then we can do the same thing that we did last time. We just sample elementary tensor products according to this distribution and empirically average them in the hope to get ever more accurate approximations of our tensor, right? Really a straightforward generalization. And the 2 extreme examples I mentioned before also generalize. Kind of one of them is you can still do tensor coordinate sampling. Now, like the dimension is much, much larger. It's like d to the n because I have n tensors. Actually, it should be d squared to the n because I have matrices here. And then I just sneak in like 1 over the overall dimension of the tensor. I compensate for that, and then I sample uniformly. And then I have, again, a very simple Monte Carlo sampling procedure. The sampling is very cheap. but the convergence is even worse than in a matrix case, just because it's such a high order tensor. And on the other side, on the other extreme, I can also generalize subsampled SVD to subsampled CP decomposition. If I were able to compute the CP decomposition of a tensor, it would give me a different kind of decomposition into elementary tensor products. And then I could use kind of these, the CP eigenvalues, in order to sample from them and do accurate approximations. But here again, this is a very good way to approximate the tensor, but it's also even much more expensive than in a matrix case because the CP decomposition is very hard to compute and it's NP hard in general. So kind of here we pay too much on the sampling side, I would say. And now I would try to argue that kind of like the interesting Monte Carlo schemes for tensors are somewhere in between. And the classical shadows of quantum systems, that is kind of the name of my talk, and also that I tried to explain in the abstract, is one such Monte Carlo approach to decompose large tensors. And kind of what we look at would really be like kind of n-fold tensor products of Hermitian d by t matrices. In quantum language, that would be n qubits, and typically d is 2. Then you have the qubit, the fundamental limit of number, fundamental carrier of quantum information. And what we want to do is we want to decompose a big tensor into kind of a sum of elementary tensor products. And note that the axes here are always all the same. So I kind of want to use the same matrix basis, the same matrix frame for each of the tensors. I don't want to treat them separately. I kind of want to use the same frame everywhere. And then I will have like kind of a probability distribution over them, and I want to use them to sample accordingly. And this will be kind of the hard part of the sampling procedure, because it's not necessarily easy to take a general tensor and to decompose it into this form if you have a fixed matrix basis or a fixed frame for each tensor factor. But we will construct our frames, our xi's, precisely in such a fashion that kind of sampling from this distribution is the same as kind of taking a quantum system comprised of n qubits, where this T describes the correlations between these systems, and do very, very elementary single qubit transformations. These are kind of the simplest computations you can do in a quantum hardware. And then afterwards, you perform a quantum mechanical measurement. And this procedure will be the same as sampling once from this distribution. And so we kind of have a hybrid Monte Carlo sampling scheme where like the actual Monte Carlo factors are very easy. They can be stored efficiently and manipulated efficiently. And the hard part is in sampling, but the quantum computer will do that for us. And so that's the overall idea. Okay. And so
can I interrupt?
Actually, the only question that remains after this description is kind of what kind of frames, what kind of matrix bases should we use? And here, I want to like kind of
Richard, sorry to interrupt. There was a question in the chat.
Yes, please go ahead.
Okay, maybe Holger, you want to ask yourself?
Yes, yeah.
Hi.
Hi, Richard. I've actually, well, maybe it's a stupid question, but you spoke about pre-processing the tensor or the matrix in order to sample it, but then, I mean, if you need to pre-process it, you should already have it at hand. So what's then the motivation to approximate it using Monte Carlo?
That's a very good point, and I actually said that, Holger. I wanted to make kind of a non-example.
Sorry? I didn't get it.
This is kind of an extreme example of what you should not do.
Okay, yeah, okay. But you speak about something in the middle, so so you don't do pre-processing for this.
What I try to say, Holger, is suppose you could do very, very expensive pre-processing, then Monte Carlo would be very good. But it would also be useless because you did the very expensive pre-processing.
Yeah, okay.
And now, why did I say that? Because here I'm exactly in this situation where I'm trying to sell a Monte Carlo technique that is very hard to sample from. But it's only very hard to sample from on a classical computer, like your laptop. But when you go to Google, for instance, and they have a quantum computer, then they can do the sampling very, very efficiently.
Okay, I get it. Yeah, thanks.
But very good, thanks. That's a very important point. You shouldn't do subsampled SVD approximation. Thank you. And so kind of the only question that kind of remains, and the important part that will connect ourselves to the world of quantum physics and quantum computers, is kind of what kind of basis or frames should we choose for each of these individual matrix spaces? Because once we pick up one of them, by construction, we can just like take tensor products and extend it linearly to the entire space. And so this is kind of our idea. We start with the space of Hermitian D by D matrices, embed it and endow it with the Frobenius inner product, because I have to talk about bases or frames now. And then once we've kind of found a nice frame or basis, we just extend the frame linearly to like all these tensor products. And that just kind of, in the physics language, this will mean we'll treat all of these qubits, all of these qubits equally and do the same thing. Okay, and what is the simplest ansatz we could do? Well, we could kind of just take as a frame the canonical basis on Hermitian matrices, like kind of EI, EJ, EI outer product with EJ, and then plus its adjoint. And then if we do that, this kind of frame is actually self-dual. And if we would carry it out, it would actually reduce in the matrix space to important sampling of the coordinates. You can quickly convince yourself that if we do Monte Carlo sampling according to this frame, then kind of like the probability of choosing the ijth element is proportional to the magnitude of the ijth matrix entry. Okay, and this is kind of very similar to the one example I gave, where we said coordinate sampling, and this is not something I want to do. I want to do something that is a bit less basis dependent, because here we're still doing important sampling in one pre-specified basis. And if you want to do quantum computation, then this is typically not a good idea to start with a fixed basis. And so the second ansatz I want to propagate, and I would actually want to use, is kind of all diagonal elements in all possible bases. By this, I mean, we don't take kind of this type of frame, but we take kind of like all the diagonal entries in the standard basis, but then we also take into account all possible basis rotations. And that's a highly overcomplete frame, because there's infinitely many unitary matrices, right? And maybe normally you would say this is not a good frame, but remember that I want to do Monte Carlo sampling in the end. And so if I want to like kind of do Monte Carlo sampling, I will just choose one of these U's at random in order to choose a single sample, and then I will do it again. So I will never have to actually produce or compute the entire frame expansion coefficients. Okay, and kind of like, why is this maybe a good idea? Kind of, it's very symmetric. It doesn't have a preferred basis. And it also has like kind of nice isotropy conditions that maybe Holger, for example, knows, because these bases kind of work well for phase retrieval, for instance. So kind of this kind of frame is not self-dual, but it's kind of almost self-dual. Kind of like if you kind of apply the frame and go back into the space, then you can do like a sequence of simple computations where you at some point use the fact that you have to integrate over all unitary basis rotations to get something. I did a typo here, it should be an identity matrix that tells you that kind of this frame is as self-dual as it can be, in the sense that it kind of reproduces the original matrix up to a scaling coefficient, but it kind of overpronounces the identity matrix. So there's kind of one direction where it's not isotropic, but it's kind of easy to correct that. And so here's like just some simple tricks on how you can actually carry out this computation. But in the end, what you will see is kind of, if you take this as your primal frame, then a dual frame will look like dimension plus one, the same frame vector, which is an outer product, minus the identity matrix. And as a small bonus result that we will need later, note that each of these dual frame vectors, matrices, has actually unit trace. And this will be important because this will tell us that contractions are basically for free. So kind of if we have these tensor Monte Carlo approximation and we want to do contractions in order to compute marginals, then this will be very, very easy, because we have elementary tensor products that all have trace one. Okay, and with that, this is kind of the frame I want to use on each of the tensor factors in order to implicitly define a probability distribution of the underlying tensor. And I want to implicitly use this probability distribution to do Monte Carlo sampling, much the same way as in the introduction. And I now really don't want to make the mistake that Holger thought I would make by kind of computing these probabilities efficiently. I would actually kind of I just tell you now what you have to do in order to get one sample according to this frame. And in order to do that, let us, for simplicity and also for relevance, assume that the overall big tensor I want to approximate, viewed as a matrix, is actually positive semi-definite and has unit trace. This will kind of help me to get to a probability distribution in the end, but it's also the relevant structure constraint if you deal with quantum systems. And so kind of what I said before is we will look at kind of all diagonals and all bases. And so in the first step, I will choose random unitary basis rotations for each tensor factor independently at random and kind of rotate my tensor in this fashion. And then afterwards, I still have to remember that I'm doing diagonals. And so I kind of contract each of the tensor factors independently with the standard basis. And this, because the original tensor was a positive semi-definite matrix with trace 1, will actually define me a huge probability distribution over all the extended computation, over all the extended standard basis vectors. And then I will sample according to this probability distribution one element. This will be one concrete standard basis vector, one for each tensor. And then in order to kind of like get the dual frame right, I have to like do the kind of like the unitary rotations in the opposite directions. Sorry, I kind of missed an adjoint here somewhere. So like on one side, there should be adjoints. And I also have to correct a bit because it's not quite a frame. And now I'm very happy that Holger asked this question before, because this is kind of very efficient on the right-hand side, right? Once I've done this type of sampling, what I have is an elementary tensor product that is actually described by very few degrees of freedom. It's a standard basis vector followed by a unitary rotation. So that I kind of, I have very efficient storage. I can contract very efficiently because it's a tensor product and each L factor is trace 1. The problem is, if I want to run this type of sampling on my laptop, it will fry very quickly. Because I start with a very, very big tensor. I have to kind of compute single tensor factor rotations, and then afterwards compute like exponentially many of these diagonal basis elements. And this would fry me. But in a quantum computing device, and this is like a caricature of a quantum computing device, of an ion trap computer, here the fundamental carriers of information would be these bullet points here. These are ions, and they kind of encode a two-level system. So kind of they would correspond to our tensor factors. And then if you want to implement such a single qubit unitary, what you would do is you would shine a laser on one of these qubits and do something there. And this is something they can do. This is like the easiest quantum manipulations any quantum hardware can do. Single qubit rotations, here, here, and here. And finally, the nasty part is all these contractions. Well, that's what the definition of quantum mechanics, the theory of quantum mechanics tells you is what a measurement looks like. If I kind of like did some manipulations of this ion chain and then afterwards perform the measurement to see in what state the system actually is, it will collapse and it will yield one of these computational basis outcomes with exactly the probability I need to do Monte Carlo sampling. That's just kind of like, I don't have time to go into details here, but kind of the theory of quantum mechanics tells you that exactly this sampling process is native for these kinds of quantum systems. And so what we actually have is now a manifestly efficient way to do Monte Carlo sampling for these types of quantum systems, where the hard part is easy, kind of like the sampling part is easy for the quantum device, and the classical part is easy for our classical computers. And now we can repeat this kind of sampling many times to get ever more accurate approximations. And the question that remains is kind of how many samples do I need to get a good idea of what the underlying quantum system actually is? And the first answer is very discouraging. If I actually want to approximate the full tensor in any sensible norm up to accuracy epsilon, I need a number of Monte Carlo samples that kind of scales like the dimension to the number of tensor factors. And that's not surprising at all, right? Because this is just the number of degrees of freedom of the tensor. But there's fundamental lower bounds to prevent me from that. But something interesting happens. Convergence happens much more rapidly if I look at partial contractions. Like if I take the big tensor and I contract away much of it. And remember that this is exactly one of these things we can do for free here, because each tensor, it's a tensor product, and each of them has trace 1. And then you can actually easily use tools from random matrix theory to prove that in order to get kind of like all contractions, all partial contractions that contract to subsystems of size R, right, the number of samples you need, well, it scales exponential in subsystem size, but it's completely independent of the big number of tensor factors, just because we've contracted. Okay. And the proof is kind of really just kind of contract to the subsystem you're interested in, let's say to just R of these n factors, contract everything else away. Then like kind of the Monte Carlo approximation will look exactly the same, but on a smaller system because it's a sum of elementary tensor products. And then there, it's again a sum of independent random matrices that have the right expectation value. And you can apply a matrix Bernstein inequality to show that on this subsystem, in this space, it kind of converges rapidly. And matrix Bernstein inequalities, they scale polynomially in the system size, which is now d to the r and not d to the n. And it will give you an exponential concentration. And then afterwards, you can just apply union bound over all possible subsystems. And what you learned is like kind of not so surprising. It kind of tells you that the important sampling procedure I introduced requires d to the r many samples in order to get all kind of partial contractions of size at most r right. Okay? And this kind of, in a physics language, this kind of means that we can perfectly resolve or accurately resolve marginalized or localized information. And in a way that's exactly the opposite of what Michael Walter, for instance, did in his quantum marginal problem, which somehow made it to the webpage of this IPAM workshop. And so I kind of turned it around. But kind of the overall idea is, if we now go kind of zoom out a bit, this tensor Monte Carlo approach gives us a very efficient way of kind of sketching quantum mechanical systems. So if you are interested in what actually happens in our quantum computing devices, we can run these simple single-qubit rotations followed by computational basis measurements to construct sketches, Monte Carlo approximations that scale exponentially only in subsystem size, and then kind of use this to get an efficient classical representation that allows us to fully understand what kind of localized things happen there. And we can understand all localized things at once. And so on a high level, you can really view this as a very efficient quantum to classical information converter, a bit like an analog to digital converter. And it's actually surprising how many things you can do with that. Like the first application, and I think this is the only one I will actually sketch, is that you can really speed up state-of-the-art quantum computations. And these are typically hybrid computations. We have kind of like classical computer, where you want to do like some machine learning or something like some stochastic gradient descent, but like on an exponentially large space. And so you have like very expensive subroutines, and you try to run them on a quantum coprocessor in order to kind of solve certain problems. And then you kind of like use your quantum coprocessor to kind of like estimate certain features or like kind of a right direction to go to. But then afterwards you have to, and then afterwards, you kind of have to read out the quantum information to power or drive your stochastic optimization. And so you kind of have a step where you have to read out quantum information efficiently. And that's precisely where this tensor Monte Carlo method shines. And here, just like for reference, kind of here is like the naive method of how you would read out the quantum information in one such application, where we have a log plot of like kind of the number of measurement repetition, the cost, the readout time over kind of the size of the quantum coprocessor. And the naive extraction for this particular example would scale horribly like this. Other proposals by Google scale like this. And these tensor Monte Carlo procedures that I kind of showed you scale like this and can even be improved to scale like this, just because basically the actual system size doesn't matter if you only care about localized information, which is the case in this particular application. And then in ongoing work, we started combining these efficient quantum to classical converters with classical machine learning techniques, like classical kernel methods for supervised learning, or kind of harmonic analysis methods for unsupervised learning. And we saw that this gives you the potential to train classical machine learning techniques based on data obtained from quantum experiments. And that can be very empowering. And we actually did several examples that we are going to publish soon, where we show that this really makes a difference, and we can efficiently train kernel methods, for instance, in this example, to classify topologically protected quantum phases, which is considered to be very hard by purely classical means. And I'm very happy and excited to talk about these things more in the breakout session, because now I have to wrap up. And I just quickly want to conclude I took you on a short journey where I started with something very, very simple, just tensor Monte Carlo techniques. And I tried to convince you of like one instance of this tensor Monte Carlo technique, which looks alien at first sight, but in a way it combines the best we have regarding classical computers and an efficient tensor product structure to store things with operations that are very difficult on a classical machine, but native on a quantum machine, in order to get a hybrid protocol that allows you to do very efficient tensor Monte Carlo approximations of tensors that describe quantum systems. And these then form quantum to classical converters that allow you to do cool things. And I want to emphasize this also with rigorous theory support. I gave you a small theorem where we showed that the approximation will be good if you look at these subsystems. And if you know a bit about like theoretical machine learning, you can combine these convergence results with powerful theorems from learning theory to actually prove that these kind of plots I didn't really show have to work. And with that, I'm at the end, and I want to thank you very much for your attention, and also very much thank you for the opportunity to speak here.